Welcome to the preview, or I guess you could say the review session for test 3. Um, let's see. We can do this the usual way. If you want to just ask a question, put it in chat, or you can just ask, through the audio. Anybody want to get us started? #401 number 6. Let's take a look at that. So I'm gonna go to my Edfinity. #401 number 6. Alrighty, I'm going to share the screen. This is #401 number 6. Find the absolute max and min function values of the function. In this case, it's x minus 2 times x minus 5 to the third power plus 7. And we're given 3 different intervals. So let me copy this. Now your intervals may change, your function may change. There might be slight changes. Uh, all right. So go to my Okay, the first thing I would do on a question like this is I would actually graph it. Let's see what the thing looks like. So I'm gonna go to Desmos. I'll bring that up here in a moment if we get it typed in. So I'm going to graph it without any bounds on it. I'm just going to put the function x minus 2, x minus 5, quantity cubed, plus 7. Okay, that's looking pretty good. I'm going to share the screen again. And there you go. So you can see the picture starting to take shape here. Clearly, there's going to be a min way down here at the bottom, and I get 2.75. Now, I don't know if that's just me where I'm clicking or if it's exact. So that's where the analysis comes in. And then also note that we're going to have some bounds. So for example, one way to enter bounds if you want is to use the squiggly brackets, and you go, for example, between 1 and 4. And what that does is that just gives you this part between 1 and 4. And you can see 1's way up here at, come on, way up here at 71. All right. Okay, so anyway, we have a sense of what the picture looks like. Let's do it both ways. Let's do it analytically as well. Now, we've already done it graphically. You want to take the derivative of this thing. And, well, to be honest with you, we've got a cube in there. I'm not so sure I want to. Let's see, do I want to FOIL this all out first and then do the derivative? Or I'm kind of asking that to myself. I guess since the question just asked for the absolute min and max values, I guess graphically would have been sufficient. Let me just show you the derivative. I'm going to go ahead and do the product. Might as well let's just jump into it and see what happens. So the first times derivative second plus the second times derivative first, which is 1, and then the derivative of 7 is 0. All right, so then let me see if I can do a little bit of factoring here. I can factor out an x minus 5 squared, and on the inside it leaves a 3, x minus 2 squared. Oh, my bad, x minus 5. Actually, I screwed it up. All right, let's just do it again. So x minus 5 squared. Oh yeah, so 3 times x minus 2, and then to the first power. And then over here, I have an extra x minus 5. Actually, this has turned out pretty nice. All right, so this is not too bad. I thought it was going to look bad, but so I have 3x minus 6 plus x minus 5. So that's going to be 4x and then minus 11. All right, that's not too shabby. All right, so that's the derivative. And if I set to 0, so I'm looking for where it has horizontal tangents. Um, one answer is going to be x is 5. And one answer here is going to be x is, what, 11 over 4, which is 2.75. All right. Now, interestingly enough, if you to check whether you have min or max, you have a couple of options here. You can do the second derivative. I'm not so sure I want to mess around with that. Or you can just do the first derivative, and what you do is you look for sign changes in the first derivative. So I'll just, like, for example, if I pop in a 0, the 0 here, that makes a plus because negative 5 squared is plus. That's going to be negative, so this is going to be negative. If I pop in, let's say, a 3 in the middle, that 3 minus 5 is negative, so that's positive squared. 3, that's going to be positive, so positive. And if I put in a 6, everything is positive. So actually at 5, there is no sign change in the derivative, so it's not a min or max. 2.75, we have it's dipping down and then going up, so it's a min. Okay. Now I'll pause here. Is there any questions with what I've done? I know I ran kind of fast. I can always review parts of my steps. Any questions?
And no question, but the 5 is outside the interval of 1 and 4 too. That's another way of looking at it.
Right. I'm doing this unbounded at the
Okay.
moment. Because actually in some of the later intervals it includes 5. So so if for the unbounded case, we're going to have a single min at 2.75, so x is 2.75. We're going to have basically a ledge at 5. I have no other word for it. And you saw from the graph had kind of this dip down and then it came up and then it ledged and then it went up again. So that's the general shape of the graph. Now to get the functional values, let me go back to decimals here. So at negative 2.75, the min is about negative 1.543. At 5, well, let me take off the bounds here. It's going to be 7. So the minimum value of the function is negative 1.543. It occurs at 2.75. This is the unbounded case. In the bounded case, where we tack on the uh, interval, let me bring that up that I had just a moment ago, x between 1 and 4. And well, I mean, again, you can kind of see we have the min here still down here at the bottom, 2.75, negative 1.543. And then the max is going to be way over here at the left end point, which turned out to be 1 and 71. All right, so in the interval 1 to 4, the max is at 1 and 71. I'll go to my paper here in a moment. The min is at 2.75, negative 1.543. If I just kind of goof around with it a couple more, let's do the other one. It was between 1 and 8. All right. Well, it looks like, again, let me zoom out. Looks like the min doesn't change, but the max is way over here at 8. That's looks like 169. Yep, sure enough. And then between 4 and 9, oh geez, I have to even go higher. So, of course, I can always just plug the number in, but this is fun. All right, it's going to be at 455. So the max will be at 455. Let's go back down here and see what the rest of the graph looks like. Interesting enough, it cuts off the dip here. So the min occurs right here at 4.5. And again, this little ledge here doesn't really give us anything. All right. That's about it for that question. Any questions on this question? Just to summarize, let me go back to the affinity question. Um, I hate to, I agree, you can probably get away with this problem just doing it graphically, and I don't really have any problem with that. The problem with, just be aware of Desmos. You'll probably have noticed that when you put your mouse a clicker on the graph, you're not always guaranteed you're exactly at the right point. That's one of the issues. That's why doing it analytically helps. So I would suggest to graph the curve, get a sense of what you're expecting, and then do the analysis like I did on the piece of paper here and make sure everything matches up. All right. Again, any questions on this? Okay. Hang in there. All right. So let's look at a couple of optimizations. I'm going to go to my affinity again. Now this one we just did as an optimization. I'm just kind of scrolling through. Let's look for a word call. That's 4.1, maybe 4.2 has something. For average values, which is good stuff to know. We can always jump back. I'm looking for some word problems here. I don't remember which side. I think let's try 4.3.
4 or 5, I think is what it is.
Okay, I'll take a look at 4.5.
Realize anytime you're taking a derivative, you're optimizing something, right? No matter.
It's the major step in the process of optimization. Yes. I mean, it's
The only difference is that you're taking one equation and you're plugging it into another. For it.
You're generating critical values from the derivative. You actually have the function, the first derivative, and the second derivative. And you can use those tools to generate or determine min and max. So yes, you will be plugging in outputs. For example, you get a critical value from function from the derivative. Well, you plug it into the function to get the actual point, for example. So there's a lot of, I guess you call it cross-pollination.
Gotcha.
Let's do this fence one right here, number 4. Are we cool with that one? I'm just scrolling to see what we got. You got a video for the box question, then you've got another one for the store. So let's do the fence one, since it doesn't have a video with it. All right, so I'm going to do number 4. This is 4.5. And a fence is to be built to enclose a rectangular area of 320 square feet. So I'm just going to jot down the information. The fence along the 3 sides is to be made of material that costs us $3 per foot. And the material for the fourth side costs $14 per square foot. Find the length and width such that obviously W is less than L, that is most economical to construct. So we want to minimize cost. Okay, so I'm going to go to my okay. And I've drawn a picture here. It's the greatest picture ever. It's a rectangle. I marked in 320 square feet in the middle, width and length. And I just kind of lightly drew in 3s on the 3 sides and then 14 on the 4th side. And you know what? It doesn't matter actually where you put them. I think on a common sense, you would probably, if you're trying to minimize cost, I think the 14 would probably go on the width. Wouldn't you agree? So I'll exchange them on the short side. But again, it doesn't matter. The cool thing about this is the math will take care of itself. All right, so let's see what's going on here. First of all, let's come up with a cost function. It's going to be 3 times L plus this over here is 3 times W, and then this 3 times L, and then this 14 times W. And let me combine those up. I get 6L plus 17W. So I have a cost so far in L and W that, but now here's the deal. I have too many letters, all right? So I'm gonna relate L and W. So come over here. We know that length and width times each other equals 320. So I can actually exchange one after the other. And again, it doesn't matter. Let's do L is 320 over W. So I'll come down here. And suddenly it's starting to take shape. Now I've got a single variable function. Let me clean it up just a tad. 6 times 320 is 1920. And then we got 17W. So this is entirely now in terms of a single variable. And again, you want to minimize this. If you wanted to, you could go ahead and graph it right now. Notice that I think it makes sense. W has to be at least 0. Okay. So no negatives. Doesn't make sense to have negatives. Okay, so you could graph it right now and get a sense of the picture if you wanted to. I certainly encourage that. I think I'll just, since I've already got this sheet up, I'll just go ahead and continue on with the analysis. Now I'm going to differentiate. By now, hopefully you're comfortable with the 1 over x derivative. It's negative that, so the 1920 is just going along, plus 17. And then let's get a common denominator. Just like that, okay? And then we set this to 0. And when we set it to 0, I'm going to write it just slightly different. I'm going to move the order. When I set it to 0, I don't have to really worry about, I don't have to worry about the bottom being 0 because W is already not going to be 0. I just need to worry about the top. So I set this to 0. And then I just work it out. I get W is squared is 1920 over 17. When I take the square root of all that. Now I've noticed that in Affinity, sometimes they leave it in this exact form, which it's awful. It's nice of them, but it's confusing. So go ahead and just work it out on your calculator. So I get about 10.627. I'll take it 3 decimal places. And I guess it's feet. Now that's not the answer. That's part of the answer. Remember, we wanted to find the most economical. First of all, we wanted to find the dimensions. So I know that if W is 10.627, now way back up here, let me bring it down here. I had the relationship up here. So then the L is 320 over the 10.627. Let's see what that gives us. 30.111 feet. So it looks like the dimensions will be 30.11 feet by 10.627. So that's what you type in for your answers. If you wanted to figure out the cost, take this W value, this 10.627, and put it into the cost function here. Let's do that. I'm sorry for the mess, but let's go ahead and just work this one out. Give me a second here. So I'm just popping it into place. So negative 1920 divided by 10.627 squared, and then plus 17 times 10.627 gives me 163. 66 is what pennies, so that should be your minimal cost. There we go. So that's a good example of applied optimization. I shall pause here. Feel free to ask for any questions on the follow-up. Does this help? I can go over any step if you want me to. Okay, again, let me just summarize then. It really, there's no one size fits all algorithm that does optimization. It is kind of a, I guess you could say it's a bit of a free form process. Invariably, you have to somehow turn the words into mathematics. And you're probably discovering you're probably drawing all sorts of little shapes, trying to get, use whatever geometry you can, like right here. And then just the trickiest part obviously is to get the function. Once you've got the function, you're pretty much about 90% done. But once you've got the function figured out, I mean, you could graph it right now just to see what your answer should be. All right, so in the last step, when you plugged in, why did you take negative 1920? No, I actually plugged it in back in the original function. Oh, you know what? You know what? That's right. You're right. I took the negative. Oh, my bad. All right. Ah. No, I'm plugging it into the function. That's an error. Let me redo that. Fortunately, my calculator, I can just bring it up and take out that 20. Yeah, it only adds 30 bucks. So the moral of the story is don't hire me to put in your fencing. There we go. Sorry about that. Thank you for that catch. All right, we have a question here for number 5-2, number 10. So I'll tell you what, I'm gonna go ahead and move on from this. We can always go back if you want to look at more of optimization. Yeah, I would do it cheaper, but it would be wrong. There'd be a whole new fence. All your animals would escape. All right, let's see. Number 5, number 10, 5-2. Let me go to Desmos and find, I'm sorry, not Desmos, Infinity and find it. 5-2, number 10. Oh, okay. That's a lovely one. Share the screen. 5-2, number 10. You copy down the information here. So we're getting into integration. You are told that the interval between 10 and 14.5 of some function is 1, between 10 and 11.5 of that very same function is 5, and between 13 and 14.5, that function is 6. And we want to know what the integral between 11.5 and 13 is. And then once we've got that figured out, then they're just being funny with us now. I'll copy it. It'd be f of x minus 5. Now mine has a 1 in front of you. You can see it right there. I think it's kind of boring. I'm going to put a 2. All right, so I'm going to, all right. Definite integrals tell us area. These are areas. Now, if I have, I don't know what the graph looks like, but you know what? I can make some inferences here. The whole interval is the 10 to the 14.5. What's happening in here is you have them being split up. You have them being split up into the 10 to 11.5, 11.5 to 13, and 13 to 14.5. Now we're given information. We're told the whole area is 1. Okay, we're told that the area here for 10 to 11.5 is 5. And we're told that the area here between 13 and 14.5 is 6. So naturally the question is, what's the area here? Well, they're just going to add up. So it'd be 5 plus x, we'll call it x, plus 6 equals 1. And then, so you get x plus 11 is 1. So that means x is negative 10. So that means the area between 13 and, I'm sorry, 11.5 and 13 is negative 10. Now I'll pause and then I'll go to this one here. But does that make sense what I did there? This is one of the properties of definite integrals. You can split apart a region into subregions. Okay, cool. Now, there was a follow-up question, and they're basically just doing a lot of weird junk to it. So I'm going to show you how to work it out. First of all, you can distribute an integral, and you can factor out any constant multipliers as coefficients. In fact, I can notice I distributed the integral between the first term and the terms, and I actually pulled out the coefficients. And so that should be the x right here. Okay, now also note that the bounds are reversed. That means you negate what you get here. So when the bounds are reversed, you negate whatever the original value was. So that this negative comes as a result of the bounds being reversed. Okay, normally you don't have the higher bound on the bottom, but sometimes it pops up. So that's all you do. You just swap the bounds. It just negates the integral. Now over here, this one's kind of an interesting one. When you have integral dx, it's almost like you're integrating 1. That's actually what you're integrating. You're just integrating the function 1, which is just a straight line. And the area would be, well, normally it would be 1.5, but we're going backwards, so it would be negative 1.5, because that's the difference between 13 and 11 and a half. And so let's just clean it up. This is 2 times 10. This is plus, and then 5 times 1.5 is 7.5. So it's 20 plus 7.5. And you get 27.5. Okay. Alrighty. Again, I'll pause and feel free to ask follow-up questions. Are there any follow-up questions on this one? The video lectures definitely had more steps than what you did. You know, that probably doesn't surprise me. I think sometimes when we create videos, we're trying to cover every, and unfortunately, we start to yeah, I guess we're trying to cover everything because we're trying to make everybody happy all the time. A lot of times you can strip this stuff down, and that's what I'm doing here. I'm not taking shortcuts necessarily. This is legitimate math. But I think I'm trying to help you guys see the geometry and see the picture. And again, definite integrals represent area. And all we're doing is we're taking a main integral, the original one up here, and we're just subdividing it into 3 little parts, and then figuring out the one that we don't know. All right. How'd you get the area of the integrals? That was the given one. These were given, if that's what you're asking. And then down here, these are just the unknowns. This was unknown, but we inferred it from what was given. So again, definite integrals are area. You know, as you move through, you know, ironically enough, you can boil down calculus into really just a couple of very basic concepts. Derivatives are slopes, integrals are areas. That's calculus right there in 10 words or less. Okay.
Can I ask a quick question?
Yeah, sure.
On that previous problem, I keep getting like 361 for the cost.
For the, no, let me just double check the math.
Six L plus 17W, and then you just put the length and the width in there, and it looks like it's coming out as 361.
Okay, I'm gonna use my given, oh, you know what? Oh, yeah, I used the proof. Yeah, I see what I did wrong. I actually conflated both the derivative and the original function. That was not good of me.
Oh, so I'm not going crazy then.
Well, you might be going crazy, but it's not with this. Yeah, you're right, 361.33. All right, again, this is why I went into math and not fence constructing. I would have lost.
Okay, I just wanted to make sure I wasn't missing anything. So
All right.
thanks for checking.
No, you're right. I'm not sure how I'm gonna handle that. You know what? I don't know if I can do the edits in YouTube. I'll figure something out. I'll put it in the reading. All right. All right, so let's go over a couple of the absolute value ones. So when I teach Calc 1 in person, we actually spend quite a bit of time on the geometry. I really try to stress the geometry. So for example, the absolute value function is a famous one because it does have some nice geometry. The basic function, as you recall, just looks like a V. That's the absolute value function. Now, if I were to integrate the absolute value function, let's say from -1 to 3, I don't need any fancy math. I just need to come over here, look at my picture, figure out what my bounds are, and then just recognize that I have two triangles. One triangle, the left one is the area is 1/2 base times height. And then the other triangle here is half, again, triangle, base times height, 3 times 3. So you get a half. What do you get here? 9/2. So you get 10/2, which is 5. There you go. You're done. All right. So that's the basic case. Now, if I get fancy here, let's say I do, how about -2 to 10 of, how about 3, absolute value of 3x, take away, I don't know, how about 12? Okay, that one's fancier. But it boils down to you basically have a couple of triangles. In fact, you can kind of get a sense of the picture here. You know that the vertex is going to be at 4. And we could actually just plug in some values. At -2, I get -6, take away 12 is -18, but then I get +18, so it's going to be way up here. And then at 10, I get 30, take away 12, which is 18. And you know what? That's kind of boring. Let's do, how about 11? Because I wanted to get some different numbers here. So let's do 11. So 33 take away 12 is 21. And absolute value of that is close to 21. So now you have a graph that looks like this. And again, it's just a couple of triangles. And you just look at the two triangles. This triangle here, the area is half, the base is 6 and the height is 18. And this one here will be a half, the base is 7 and the height is 21. And I'll just punch those out real quick on the calculator. This is 54. 7 times 21 divided by 2 is 73.5. And then just add them up and you get your answer. 127.5. That's all you do. Okay, so that's an example of just using geometry. Another one that I'll just draw it on the picture here is that sometimes I'll just draw a graph, try to do it somewhat accurately. So you might get something that looks like that. That we'll call this guy g of x. And then this is just numbered off in the usual way. So I might ask you, what's the definite integral between 1 and 3 of g of x dx? Okay. Well, I'm looking at my picture here. Between 1 and 3, it's a rectangle, and then it's a trapezoid. But the trapezoid can be broken down into a rectangle and a triangle. So if I just kind of look at my picture here, the rectangle is base 1 and height 3. This rectangle here is base 1 and height 2. And this guy's going to be 1/2 because it's a triangle. Base 1, height 1. So we get 3 plus 2 plus 1/2 is 5 1/2. Okay. That would be an example of just using geometry in this way. And also, you know, if you happen to have a part of the graph that's below the x-axis, you count those as negative areas. Um, I think, I don't know if you have it in your homework. I don't think you did any circles. But just in case you did, the formula for the area of a circle is pi r squared. And then if you're having half a circle is half pi r squared, for example. And so you just have to kind of take portions of the circle to figure out your areas that way. I don't know if you had any of those though. Can you do an example of it going, there was a half circle? All right, let's do one. So we have a question. Can we do one going into the negatives? Yeah, we can do that. Tell you what, I'll combine the two. Come on. And then we want to do one with a half circle. That was 5(2)6. So let me bring it up. I'll kind of combine them. So 5(2)6, since I already have it up here. Oh yeah. Let me share the screen. Evaluate the integral below by interpreting it in terms of areas. In other words, blah, blah, blah. All right, so I'll just copy it. -7 to 7 and square root 49 minus x squared. All right, that's what it is. So I'll tell you what, let me do this one real quick. This is the formula for a circle. The bounds agree with the edges of the circle. So you're just getting a half circle. So the area is 1/2 of pi r squared, but you got to be careful here. Well, okay, we got it because if it was a full circle, I would just use pi r squared. So it's 1/2 and pi, and then 7 is the radius. So you get 49 halves pi. And that's a good answer. You can leave it like that if you want. If you like decimals, you get 76.97 square units. Okay. Let's do one where we combine them both. Let me make up a function here. Do this. Call this crazy thing h of x. All right, so that's a part of a circle. And then you got a couple of straight lines. So let's do the integral from 0 to 5, h of x dx. Okay. And so we're going to break it up into 3 parts because that's the natural breaks here between 0 and 2, 2 and 4, 4 and 5. So between 0 and 2, well, that's a quarter circle. And the radius is 2. So 2 squared is 4 divided by 4. You just get pi. But we got to put a negative in front of it because it's below the x-axis. So this part is actually -2 pi. That's the area. Okay. Everybody catch that negative there? Between 2 and 4, that's a triangle. Half base times height, 2 times 2. 2 times 2, oh, so we get 2. All right. And then this between 4 and 5 is also a triangle. I didn't draw this so great, but that's close enough. It's going to be 1/2 base times height, 1, 2 times 1, and we just get 1. So the answer is, you take these all together, you get 2 plus 1 is 3, take away pi. And that's your final answer. And the overall answer, again, if you want a decimal, it's actually a negative. It's negative 0.14159, blah, 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 42. So that means there's more area below in this graph right here, there's more area below the x-axis than above, just by a little bit. All right. Does that help? Questions on that one? Um, 4-5 number 7 and 4-3 number 4. These will be the last two I do. I am rushing a little bit. 4-5 number 7 and 4-3 number 2. So 4-5 number 7, 4-3 number 2. All right, so 4-5, let's see, 4-5 number 7. Yeah, I'll set it up. So 4-5 number 7. We don't have a paper. How about that? Hold on, let me concentrate. 4.5 number 7 is x minus y squared equals 0. We want to find the point on the parabola closest to 0, 3. Okay, so let me just show the screen very quickly. That's the question right here. So just work it out real quick. Basically, I'll show you what to do. You set up a distance formula. The distance between, you have a point x, y, and 0, 3. So the distance will be the Pythagorean formula will be x minus 0 squared plus y minus 3 squared. You can clean that up just a tad. Now you don't need the y. Actually, check this out. If you, I just realized, you know what? I'm gonna do this. I'm gonna let, if y squared equals x. So in fact, I'm gonna do it this way. I'm gonna do it in terms of y. So x is y squared. That way I don't have to mess around with the radical. So you're going to get a strange looking, I'm going to FOIL this out. You're going to get y squared, take away 6y plus 9. And then you just take the derivative of this. And again, I'm rushing a little bit, but there's some nice shortcuts here. The derivative of this right here goes on top. It's going to be 4y cubed plus 2y take away 6 equals 0. No, you know what? You get a cubic. Interesting. You know, the only way to do this, because there's no easy way to factor a cubic. You have to use a calculator to find what y is. Okay. And you can do this on Desmos too. And I think, you know what, honestly, if you did this, if you let x equal square root y, it would be a mess. All right. All right, so 4-5 number 7. I'm just going to kind of leave it hanging here because again, I'm trying to finish this before the test starts. You're going to have to use a calculator to determine this root. That'll be your y value, and then just back substitute to get your x value. Okay, and then the last question was 4-3 number 4. Let me bring it up real quick. Four, 3 number 4. This thing's got all sorts of stuff in it. All right, again, I'll just let me show the screen. And we can this can be greatly reduced in terms of the amount of area here. So I'm not going to do the whole question. because I don't have time, but I'll show you some tactics here. First of all, graph it. All right. So first thing, just graph it, get a picture. Look at where its mins and maxes are, all right? Find the first derivative, just take the derivative. So this one's going to use the quotient rule, so bottom derivative top, minus top derivative bottom, all over bottom quantity squared. You get e to the 2x plus 8 e to the x, take away e to the 2x, e to the x plus 8. I'm going to stop this. I kind of need to keep it here. I'll go back and forth. You get 8 e to the x, e to the x plus 8 quantity squared. That's your derivative. Now, okay, so now you're getting questions here like, where is it increasing? Where's the min? Where's the max? Well, gosh, if you set this thing to 0, you're not going to get any critical value. Or no, you won't, because e to the x is never 0. All right, so this thing might be increasing on the whole real line now that I think about it. Now, if you want to do the second derivative, to do the concavity, again, I hate to punt on this one, but I don't have the time. I'm just going to say this on a question like this one, you can answer a lot of the questions graphically. I don't have any beefs with that. I think it's all part of the problem solving process. This particular derivative just is never 0. In fact, it's always positive. So it appears to me that this thing the function is always increasing. Okay. It appears that it's probably going to level off. So it probably has one point of inflection, and it's probably concave up for half the graph and concave down for the other half. But again, I would graph it. I didn't do the graph. You know what? This will be the last thing we'll do. I'll graph it. Because let's take a look at this thing. I'll bring it up here on the screen in a second. Yep, there it is. Okay, I'm going to share my screen. There's your graph. That's the exciting graph. Okay. There is no min or max. It has asymptotic behavior. It's always increasing. There's no decreasing. The point of inflection is going to be somewhere in the middle here. Now, this one you're going to have to do analytically. You are going to have to perform the second derivative and set it to 0. But you can kind of eyeball it. It looks like it's probably somewhere in this region right here. It's very difficult to get the point of inflection exactly just by looking at it. I can tell you it's going to be somewhere around there. It might be 2, you never know, but just to be safe, work it out. Now let's just suppose it's 2. All right, fair enough. Then it's concave up to the left of 2, concave right to the right. Concave down to the right of 2. Okay. So again, just to emphasize, a lot of these questions can be done concurrently. So graph it and then do your analysis just to make sure everything matches. If you just try to do the analysis by itself, it's like trying to do math in the dark. You're totally dependent on the math. It's nice to have a sense of the picture like I have here. All right. Okay, gang. I am going to end this because I wanted the test is starting up here. Again, thanks for hanging in there. Gosh, this has just been a crazy few days. It's going to be a crazy more couple days. Be checking your emails, and because I am going to be sending some stuff out regarding like test reviews for the final. And good luck on tonight's test, or it starts tonight, goes through tomorrow. I will be circulating grades early Tuesday morning. All right, cheers.